Welcome back. We've talked about these 5 sorting algorithms. And by now you should know that merge sort and quicksort, although they're harder to implement, are the most often used algorithms in real life because they use divide and conquer to get us this O of n log n performance boost. But can we beat O of n log n? And here's the thing. Mathematically, it is impossible to improve on this. If anybody comes up with an algorithm that is faster than this, they're gonna be very, very rich. Mathematically, it's impossible because O of n log n means that we have to sort by comparison. All of these sorting algorithms have to compare every number to each other. But there is one exception to this rule. You can improve this if you don't make comparisons. Huh? What does that mean? There's a small section of inputs that we can actually beat O of n log n. And these are called non-comparison sorts. And you'll most likely see counting sort and radix sort. But what does that mean? Counting sort and radix sort is an entire different way to think about sorting. With comparison sort, we decided the order of the numbers based on asking the question, hey, is this element bigger than the one over there? What about the one over there and over there? And we just kept doing that. Every number got compared to each other. Non-comparison sorting does it a little bit differently. We're going to use the way that numbers and data is stored on our computers in zeros and ones and take advantage of that fact to sort things. Now, this can get pretty complex. And as you can see here in this paper, just looking at the diagrams and, for example, radix sort here and how we store numbers in zeros and ones, we can use this knowledge to actually sort some things. I'm going to leave resources for you if you want to get really technical and into this topic. I do warn you, it can get a little bit mathy. But the one thing to note here is that these type of sorting algorithm, counting sort and radix sort, only work with numbers, specifically integers, in a restricted range. So if you have only numbers that you want to sort, and the range of those numbers go from, let's say, 0 to 100, that is a small range, then you would use something like this to make things really fast. But it wouldn't work on any type of data. It only really works on numbers because of the way numbers are stored in memory. You see, unlike something like merge sort or quicksort that are universal, that is, they can sort any type of data, things like counting sort and radix sort is only useful for fixed length integers. But they are able to beat the speed of O n log n. And as you can see here, bucket sort, radix sort, counting sort, in their average cases, have O of n plus k, O of nk, O of nk. What n and k means is beyond the scope of this course, and some argue that in the end, this actually still turns out to be pretty slow. I'll leave resources for you, like I said, so you can read up on them, but the only thing you need to know about these is that sometimes if you have numbers that are within a certain range, it could be faster than quicksort or merge sort. So now that we know this, let's do some interview exercises based on sorting to solidify what we just learned.